Good afternoon, everyone. Thank you for being here. I'm Incheol Han, the leader of Quantum Project team. I will be facilitating today's forum. Let's officially begin the 9th Quantum Computing Biohealth Forum. Since we held the first forum in June 2022, we have now reached 9th session. This forum holds special significance for a couple of reasons. First, we are currently in the trial service phase of Korea's first quantum computers, which is installed in Yonsei University, which was additionally, this is a momentous occasion as our newly organized quantum project group has officially begun its activities, making today's forum even more meaningful. We are also delighted to welcome Professor Kenneth Wells, who will be delivering a special lecture today. Professor Wells brings intensive and experience in quantum computing and medical research from the Cleveland Clinic, where an IBM quantum computer was installed early last year. Now I'd like to invite Professor Jae-ho Jung, Senior Vice President of South Science Park Project and the Director of the Quantum Project Group, to the stage for some welcome remarks.
네, 안녕하십니까. 방금 소개받은 정재호입니다. 오늘 우리가 스페셜 게스트를 모셨습니다. 오늘 조금 의미 있는 날인 게 몇 가지만 여러분들 말씀드리면, 일단 연세대학교가 국내 최초 그리고 전 세계에서 5번째로 범용성 상용화 그레이드의 퀀텀 컴퓨터를 지금 설치가 끝나서 아마 다음 주부터는 연세대학교 교내에서 사용하실 수 있도록 저희가 안내를 해드릴 겁니다. 그리고 이제 이 컴퓨터를 기반으로 우리 대학의 교육과 연구 그리고 산업화 역량을 고양시키기 위해서 이 사업을 전담할 학교 내 조직이 만들어졌고, 방금 전에 소개를 하셨던 우리 한인철 팀장님이 그 양자 사업단의 양자 사업 추진팀을 총괄하고 계십니다. 앞으로도 연세대학교 양자사업단 그리고 김재원 원장님이 책임지고 있는 양자정보기술연구원에서는 여러분들과 함께 양자컴퓨터 그리고 바이오헬스 관련한 지식의 장을 계속 열어나가도록 하겠습니다. Welcome to the 9th Yonsei University Quantum Computing and the Biohealth Forum today. And we are grateful for today because we have world-renowned chemistry and esteemed scholar in the field of chemistry. And I'm not actually quantum guy. I'm such a naive person, but I understand that how the quantum computing is useful and promise us a brighter future by solving the unsolvable problems. So this is in line with the Yonsei vision. So our new president of Yonsei University announced that our vision and goal is to solve the unsolvable problems for the benefit of humankind. So with that, the quantum computing in our country's first placement in this international campus is a kind of a remarkable one. On top of that, actually, the Cleveland Clinic, if you think of the Yonsei University, the name implies that it's a joint of the Yon and the Se. Se means the Severance Hospital. If you go to the Sinchon campus, there is a huge building named the Severance Hospital. You know where the name comes from? Actually, more than 100 years ago, the great philanthropist from the Cleveland, he donated huge money to build a hospital in this land. So actually, at that time, it's not a Korea, it's a Joseon dynasty. So I think there is so we named after the Severance Hospital in commemoration of his generous and visionary philanthropical money giving to the Yonsei University. So it's kind of historical legacy actually keep continuing, so that today we have the Dr. Kenneth Mertz, and he is going to give us a visionary talk about intermolecular interactions explored with quantum computers. So before I have him in the podium, just like it's a quite extraordinary thing about that the American Chemical Society, actually, they hosted the symposium in honor of the 65th birthday of Professor Kenneth M. Mertz Jr. To me, it's a quite unusual occasion, but it's kind of a commemoration of his great achievement in the field of chemistry and how he enlightened the future generations to follow his path. So with that, I'd like to invite Professor Kenneth Mertz to the podium, and please give him a big applause. Thank you.
Thank you. Thank you for those nice comments. I have to say I'm feeling really embarrassed right about now. I adapted this talk from a talk I gave in Japan, so I apologize. I do know that Seoul is in Korea, so sorry for that mistake. I truly am a little bit embarrassed. So it's really wonderful to be here. I've been to Korea many times. I counted maybe 8 or 9 times, but it was all at the airport. So on the way to different locations. So this is actually the first time I've stayed in Korea proper, down in Seoul, and I'm here with my daughter. She's 24 years old and is very much into Asian fashion and style and food, and so we've been enjoying our visiting Seoul for quite a bit. I also want to congratulate Yonsei on the installation of your new quantum hardware. I mean, that's really a very significant event, and you're one of the few locations in the world that has a quantum hardware on site. It may not be the one we choose in the end, but it's a really major milestone. So my deepest congratulations to you on this achievement. So today what I want to do is I'll tell you a little bit about Cleveland Clinic, because I get this question all the time: why does a hospital, or why did a hospital get involved in quantum computing? So I'll give you a little bit of the history of Cleveland Clinic, which goes back to, as you mentioned, to the Severance Foundation, which was also in Cleveland. And then I'll tell you a little bit about kind of my perspective on quantum computing, and then I'll highlight some research we've done that the first paper just came out on arXiv, and I'll show you where that is. And we have another paper that we're finishing now in collaboration with IBM that should be on the arXiv in the coming weeks. So with that introduction, let's see if here we go. So we have this saying, and I don't know, there's maybe a Korean variant of this, a long and winding road. So how does a hospital, why didn't MIT or Caltech do this? So how did a hospital actually end up getting into quantum computing? And it's actually quite an interesting story. So a little bit about Cleveland Clinic. It's a worldwide hospital system, initially founded in Cleveland right after World War II, right? World War II saw just amazing slaughter, and the physicians had come back from World War I and wanted to set up a more integrated hospital, and that was established in Cleveland. We have branches in Toronto, branch opened in London just recently, Abu Dhabi, and also in Florida. And you can read some of the statistics. It's one of the largest hospitals in the United States. Usually when they rank hospitals, Mayo Clinic, many of you have maybe heard that, in Minnesota, is usually ranked #1, and Cleveland Clinic is #2. And I'll tell you a little bit about their accomplishments in Cleveland. So Cleveland had several major accomplishments: the discovery of serotonin, which is important in sort of mood disorders and things like that. Kidney dialysis was pioneered at Cleveland Clinic, so this is used all the time now, saving many, many patients worldwide. Angiotensin II and hypertension. So Cleveland Clinic's really famous for heart disease. When I was interviewing and visiting, I was in there in the breakfast area, and I just bumped into a person there, and he was actually there for open heart surgery he was going to have in a few days, and he was, eating breakfast, and it turned out he was from Egypt. He, was a businessman there, and he came to Cleveland Clinic to have the surgery done, the open heart surgery done in Cleveland. So again, very famous in heart surgery area. So how did they get in quantum computing? Well, Ohio is part of the American Midwest, and the American Midwest had many factories related to the auto industry and steel and things like that. But with global competition from Japan, Korea, and many other countries in the world, that kind of industry has gone down. So there's a great interest in expanding into more high-tech areas. So there was a partnership formed between Cleveland Clinic and the state of Ohio. It's called Jobs Ohio. It's about a $500 million influx of money over 10 years. And they really wanted to create in Cleveland an innovation district. And Cleveland Clinic is the anchor of this. So you have kind of a road going in where there are various kinds of startups and companies are starting to set up shop in the area. So this really started a search for, well, we have this Jobs Ohio, who can we collaborate with? And so the logical partner, and Cleveland Clinic looked at many partners in the end, but the logical one, it was IBM. They had many interactions with IBM, with the Watson system, and they decided to continue that. So part of this Jobs Ohio, led to collaboration with IBM. And IBM needs no introduction here. Everyone, I think, is very familiar. You've just recently purchased or leased one of their hardware platforms. But this is a very well-regarded company with multiple Nobel Prizes, Turing Awards. Metal Technology is the highest award for technology in the United States. Again, the National Medal of Science recognizes great accomplishments in science. And they've actually led in patent leadership for a huge number of years, which I find to be incredibly remarkable. So they decided to collaborate with IBM. And this is, again, was a 10-year collaboration. There's, I think, $150 million is put into this collaboration between Cleveland Clinic and IBM, both in presence of hardware, so placing a Cleveland Clinic, a quantum computer, but also personnel. So I had the luxury and I'm blessed with the opportunity to collaborate with leading scientists in IBM. We actually have liaisons between Cleveland Clinic and IBM to help support the research program that I'm going to tell you about. So the aspects of the collaboration, there's research collaboration and commitments. There's a strong focus on AI, machine learning, digital technologies, hybrid cloud. The other thing that I think is really important, I think in our conversations right after lunch, is training and outreach, right? The new workforce, there's just not that many people that are trained in quantum computing and quantum information science. And this is going to be a field for the young people in the audience. This is going to be a field that's going to play a big role in your scientific life going forward, right? As this technology matures. So it's really essential to train people to use this really novel technology. In some ways, you should think about it like this is like the 1970s with integrated circuits, right? You have this new technology, and it's going to be the task of the younger generation to really figure out where this can be applied and how it can make a difference in today's world. We have a quantum program, so we gained immediate access to IBM's quantum systems. So I have access to the IBM hardware that's in the cloud. And we also had a system installed, which I'll show you a picture of in a second. And we're going to have, in the next few years, the System 2 installed at Cleveland Clinic. Overall, we're truly blessed with incredible support from IBM, both in the education, but also in the hardware. The ability of my group to come up with some thoughts and ideas and immediately try it on quantum hardware has just really been truly remarkable. And I think that's something here at Yonsei that you're going to be blessed with, right? You're going to be able to come up with some ideas, try it on the hardware, and see how this works for you. So the areas we're collaborating with in terms of collaboration, high-performance computing. So today I'll tell you about quantum-centric high-performance computing and what we could do with that. There's AI, artificial intelligence, in quantum computing. My group is heavily working in this quantum-centric quantum computing, so these two areas. And I also have several people in my group that are doing quantum machine learning, and I won't have a chance to tell you much about that today. So, but that's kind of the research areas that we're involved in. So this is the first device that was installed. It's an Eagle processor. It's identical to the machine you have here at Yonsei. Did you get the light pattern, or do you have the dark machine? You have the Darth Vader machine. Okay. So, but yeah, so Cleveland Clinic wanted a light color pattern because, you know, we're all about curing patients and seeing the light. So this is the first kind of hardware installed outside of IBM in the United States. A couple of interesting things about this. The glass is from Venice, so Venice is famous for Murano glass. The typical machine has the top is open, but they had to put glass on the top as well because this was installed in a cafeteria. So you literally can walk over and, if you want, throw a paper airplane on top of it, right? It's in a former cafeteria. So it's every now and then when I want to get inspired, I walk down and take a look at the device. So IBM, I think, and people here are extremely familiar with it, and we had a nice discussion about different hardware vendors. IBM is probably unique in the sense, and I think some other vendors are doing this now, they actually give a roadmap. And so we're here at 2024-25. This is the Eagle processor in Heron. We've had some ability to run on a Heron processor, very nice device. None of these actually have error correction explicitly on the hardware. They're all error mitigation. And I'll tell you about a unique way in which we do error mitigation with our calculations. But the important thing for me, if you look at 28, 29, 30 in the next 4 or 5 years, we're going to have hardware error-corrected devices. So right now, we have to really fight errors with our algorithms, but IBM is anticipating delivering this in this time frame. I think their plan here is very aggressive. They've hit all their roadmaps, all their targets to date. So I'm very optimistic that in not too many years, we're going to actually have this error correction capability right on hardware and hundreds of qubits. And again, because qubits, the power of these devices scale with the number of qubits, the more you have, the more power you have. But that said, we currently have an Eagle device down here, and in the future we'll get probably a Heron or a Flamingo. That's to be determined. So the other companies are involved in this. I just list a few. There's many others. We talked about several other companies. We'll see. You know, it's going to be really exciting in the next few years. Many of them had roadmaps or suggested they wouldn't have really good hardware until, say, 2030, but now many of them are saying they're going to deliver error correction in around 2030 as well. So it's going to be a really hectic, say, 5 years in the hardware side of things as well. So my group currently is working in these 3 different areas, so quantum simulations, quantum machine learning, and optimization. We sort of abandoned a little bit of the optimization because we found a lot of the sort of VQE-based methods, as I'll highlight, really cause a lot of errors to accrue and aren't very stable for the kinds of problems we want to do. So this area is a little bit kind of put to the background for right now. So again, today I'm going to talk mostly about, or exclusively about, quantum chemistry and not material science applications, but healthcare and life sciences applications. And before I jump into that, I should talk a little bit about the group. So the people that are doing this, so Daniel Kaliakin right here, Akhil Shajan, he's been driving a lot of the effort, Susanta Das and Zen, and the quantum machine learning people are Hong Ni and Gurinder. I don't have a picture of him. My funding is from the NIH and the NSF. The nickname for my group, this was actually given to us by IBM folks. We're called Team Sonic because we like to move really fast. And also Sonic, if you see, he looks like he's entangled, right? So he looks like he's behaving in a quantum way. So I wear this title very proudly in terms of my group. So, you know, it's really worthwhile, I think, spending a little time thinking about kind of where we've been and where we're going, right? So back when I was early 20s, I joined a group here that used, actually, it was one of the 2 groups in the world that had a VAX 11780 in its lab. John Popel, who eventually won the Nobel Prize, had an 11780, and Michael Dewar's group at the University of Texas. And this is, again, the Moore's Law, and you can see that basically down here in 1980 or so, this wasn't a particularly fast machine, but, you know, it was, for the time, it was incredibly fast, and it was ours. We could do whatever we want with it. Even that, we couldn't really do very sophisticated calculations. You know, benzene was a really difficult problem to calculate. But, you know, it was I think this is really a beloved machine in the community in terms of compute power. When I was towards the end of my PhD, we got a call from a company called Cray Research. And they were like, hey, you know, we have this new machine. It's a vector machine. Can you get your code working on this device? And at the time, you know, my friends in grad school all thought I was crazy for getting into theoretical chemistry because there weren't many jobs at the time, right? And so I was sort of not going to have a very bright future. But Cray came along, and this is 500 times faster than the VAX 11780, right? So benzene that maybe took a couple days to do now took a few minutes. So it was a huge, huge sea change. And then later on, parallel computing, Cray TE3E. I'll tell you a little bit more about that in the next slide. And nowadays, in the 2020s or so, we have NVIDIA GPUs, which really, you know, aren't on this graph, but this is sort of just the timing of these. And we're doing a lot on GPUs. And then I have here at the end, in 2024, we're gaining access to IBM System 1, 127 qubits. This is not to imply it fits on the Moore's Law. It doesn't. But this is kind of the current generations of machines. So a little bit about these. So VAX 11780, it's this top machine on the left. This, you know, kind of ugly looking thing, I guess. It was 0.2 megaflops, right, was the power rating. We got a hold of the Cray. The Cray was about 100, 150 megaflops, so about 500 times faster. And as an assistant professor, I got a hold of a Cray T3E with about 1,000 CPUs. Each CPU is as fast as a single Cray XMP. And I had 1,000 of them, right? So 1,000 times faster in principle. And down here, recently we've been doing some quantum chemistry on Hopper GPUs. This is a 60 teraflop machine. It's about 400,000 times faster than the 11780, right? So this is the kind of increase in power that we've had. But now this graph here shows the performance in VAX 11780 units. So basically the current CPU chips are about 40,000 times faster than, so this would be like a Pentium class chip. But if you notice, it's really plateauing. And so silicon is quickly plateauing, and we need something new to really keep pushing the boundary for compute power. So is quantum computing going to be that step forward? So let's see if I can get this movie to work. So I'm interested in healthcare, life science, computer-aided drug discovery. And so one of our goals is we want to be able to compute protein ligand interactions using quantum hardware. And the first thing you do is you look at, this is Crixivan bound to the HIV protease, and you can see you have things like hydrogen bonds. I can't really get, so you have van der Waals interactions here, some more van der Waals interactions. And then down here, you'll see some hydrogen bonding interactions. So typically when drugs bind to a protein, you're going to form dispersion interactions and hydrogen bond interactions. So we really wanted to first just ask the question, can we use a quantum computer to compute dispersion interactions and hydrogen bonding interactions? At the point where we looked at this, no one had really done this. So it wasn't known if it could be done. People had tried different things, but weren't particularly successful. So we decided that we would tackle a very simple system. We're going to tackle the methane dimer, which is the model system for dispersion, van der Waals interactions. and the hydrogen bond interactions defined by the water dimer. Again, very, very simple, but if you can't do these, you're not going to do a protein ligand system, okay? So how did this work out? So a couple things we should think about first. So in quantum chemistry, so this is a quantum chemistry application, there's two types of correlation that you need to consider. So if you think of like the nitrogenase cluster, or if you think about photonics, things that are, very, very important in the, Korean industry, this is a static correlation problem in the sense that you need to consider all the possible electron configurations for the system you're interested in. So if you're looking at exciting an electron in a double bond to the pi star, you need to mix those two states, right? So this is static correlation. Static correlation is really important in materials, photonics, many, many areas, but it's not particularly important in drug discovery. Drug discovery is not driven so much by static correlation unless you have, say, a transition metal that you're going to bind your drug to. What is more important in drug discovery are dispersion interactions and hydrogen bonding, and this is really defined by dynamic correlation. So basically, it turns out typical quantum chemistry calculations, they have a flaw, like DFT, things like that. They don't incorporate dispersion interactions correctly. Dispersion interaction is just sort of mutual repulsion of electrons. So as you bring the two methane molecules together, the electron clouds deform and move their electrons around to respond to the fact that you're bringing this other molecule that has electrons close to it. So, again, in the quantum computing area, most people want to talk about static correlation. If the only thing you can do is static correlation on quantum hardware, that's never going to get you into healthcare and life sciences. It's going to be great for material science, but we really need to be able to handle this other type of correlation. So basically, initially, we started out using something called the variational quantum eigensolver, which is more of an optimization algorithm on quantum hardware. We found, like, for this particular system, it didn't work very well. And Jay Gambetta, who's the head of IBM Computing, I met him at Cleveland at a meeting, and he said, oh, you need to talk to this group at IBM, led by Antonio Mezzacapos. So Antonio's here. Javier is here, and Mario Moto. So Javier is the first author in this paper, Mario is the second, and Antonio is the corresponding author. This is a collaborative project done with the group at RIKEN, which I had just come from. I just spent 4 or 5 days visiting RIKEN, talking to their scientists. So this paper, I think, to me, is a landmark paper. It's called Sample-Based Quantum Subspace Diagonalization. It's quantum-centric quantum computing. And instead of doing optimization, what they're doing is they're using the quantum device to pull out samples of the Slater determinants in a particular type of calculation. And I'll get into that in a little bit more. Ella she's sort of the fearless leader. She basically coordinates between IBM and Cleveland Clinic. Excuse me. And she's the one that gave this team the Team Sonic logo. So basically, we met with this team on a Friday afternoon at 4 o'clock. And for the first 6 months I was at Cleveland, we were just VQE, 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 right? And by 5 o'clock, when we finished the talk, we then had a post meeting, and we decided we're going to abandon VQE completely, and we're going to use this squeeze approach. And hopefully I'll convince you that that was a smart move. So over the weekend, we sort of got the software together. We had several meetings to think about the theoretical aspects of it. But this paper, it came out in arXiv. The arXiv's here. And the important thing is they are able to do things like the nitrogen bond breaking. And again, this is a static correlation problem. They're able to model iron-sulfur protein clusters, both 2 iron, 2 sulfur, and 4 iron, 4 sulfur. Importantly, instead of being stuck with 4, 6, 8 qubits, they were able to go up to 77 qubits. And in particular for this 4 iron, 4 sulfur, they're able to show quantum utility. So basically, the quantum approach was better than the classical approach, which is really important. So building off of this, we wanted to go after dynamic correlation. So this just summarizes things. So VQE basically is confined to very simple molecules. It's only can handle 2 qubits, 4 qubits. I think some people have gone a little bit higher in qubit count, but again, you're really, really limited, and you're never going to get that quantum exponential power using small number of qubits. And even when you get it to work, the errors can be quite large. So if you compare a VQE calculation versus a classical version of that, the errors can be 4 kcals per mole, even on 2 qubit experiments. Squeezed, on the other hand, so I'm sorry, some of these will be SQSD and others SQD. Basically, it's the same algorithm. We now call it SQD. So basically, I think this is, and I'll hopefully convince you, there's a broad range of applications using this method, even potentially drug discovery. We can routinely use circuits of 20 qubits and more. We've done some experiments on cyclohexane, which I won't talk about, up to 77 qubits. Importantly, the variation between the classical version of that calculation and the quantum computing version using SQD algorithm, the errors are less than 10 to the minus 4 kcals per mole. That's kcals, not Hartrees, kcal per mole. So essentially they're identical, and I'll show you a number of examples of where this is true. Okay, so I'm not going to go into like circuit design in detail. If people want to talk about like the ansatz, we can discuss that. If you're really, really interested in some of the super quantum information technical details, I can connect anybody with Mario Moda, and he is sort of kind of our QIS expert on this project, and he'd be more than happy to speak with you. But I'll give you sort of just a general sense of what we're doing in this quantum-centric approach. So we basically take an optimized geometry for the methane dimer, and then we use 2 programs. We use PySCF to do the Hartree-Fock calculation. PySCF, I think it's Garnet Chan's program, if I'm not mistaken. You can download it for free, et cetera, and it'll create a file that has 1 electron, 2 electron integrals in the microorbital basis set. It's called an FCI dump. In this, we're going to be doing CI, or configuration interaction calculations. We also use something called AVAS. These are going to be configuration interaction calculations within an active space. So an active space, if you think about ethylene, the pi bond and the pi star bond, that could be the active space you're studying. So in these more complicated systems, the active spaces get trickier to deal with. So having an automatic program to help you define your active space is really essential. So AVAS is a program to use. There's multiple versions of this kind of program out there to do this kind of thing, but we have to use AVAS. So then we get this FCI dump, and then we use a program called DICE, D-I-C-E. This has stochastic heat-fast CI or heat-fast CI capabilities. This is we're going to take our active space, we're going to do the CI calculation using DICE, using this stochastic heat-fast CI, and we're going to get a ground state energy. So this is the comparator that we're going to compare our quantum calculations results to. So this is all done on classical hardware using this DICE program. So in the quantum-centric approach, we do things a little bit differently. We take this and we place it onto the quantum hardware using a localized unitary couple cluster JASTRO ansatz. This is an algorithm developed by Mario Moda, so if you're interested in some of the technical details and the gate structure and things like that, he can help and discuss that with you. So what does this do? It's a couple cluster approach. You put this ansatz on the quantum hardware, and then you don't do any optimization. You don't ask it to optimize your wave function. You simply ask it to give you Slater determinants. So what is a Slater determinant? A Slater determinant is a mathematical object that tells you where the electrons are in the molecule in a qualitative sense, right? And basically, if you think about these Slater determinants and sort of doing these calculations, if you think of a molecule like propane using a STO3G basis set, very small basis set, there's about 1 trillion Slater determinants that you could determine from just propane using a small basis set. But what we do with this is we pull out about 100,000, depends on the application. Most of these will be about 100,000 slated determinants. We pull these slated determinants off the quantum hardware, and these slated determinants are informed by this LUCJ ansatz. The other thing, too, is these calculations don't use STO3G. These are done using OGCCPVQZ, a huge, a very large, chemically accurate basis set. So the calculations that we're doing on the quantum hardware today that I'm describing are using realistic basis sets, not toy basis sets. So we generate these bit strings. Now, these bit strings describe slated determinants. The important thing about these is you can apply a mathematical operation to these slated determinants and determine how many electrons that slated determinant is describing. If it's wrong, then instead of saying if your molecule has 10 electrons, it says it has 11 or 12 or 9 or 8, you know that an error occurred in your quantum hardware. So what you can then do is you can engage in a post-processing error mitigation strategy by taking these bit strings, and you can flip the bits. You can go in and say, based on, say, orbital occupancy, say, this bit I'm going to flip. And by flipping it, you go from 11 electrons to 10 electrons. So you've error corrected your quantum hardware. Error appeared, you have a clear way to do it. And this is all done on classical hardware. So then what we do is, through this error mitigation, we take our 100,000 bit strings, we usually bin it into 10K sub collections, right? So we'll have 10 samples of 10,000 bit strings. We then actually do, again, using PyCF or DICE, we do CI calculations. These are called select CI calculations in particular. And then we go through for each one of these 10, we get a result. We then take that information to help us inform the error recovery, again, by getting updated orbital occupancies. And we loop through this. I think Mario and his team, Antonio, they did typically 10 iterations. We find like 2 or 3 iterations is all you need to reach convergence. And then you end up with 10,000 CI calculations that you then compare to the ground state energy over here. So this would be a select. So basically, we're not enumerating all the configurations. We're taking LUCJ informed configurations to then do a select CI. So let's just say this CI space has 1 trillion potential determinants. We're only taking 10,000, okay? And it turns out, and I won't go into this LUCJ ansatz, there's something here that I guess even Mario, we've had conversations, don't fully understand. But it's seemingly, and IBM has showed this, at low sample counts, like 10,000, 20,000 samples, it gives results very, very close to the true result. So it basically converges very quickly. If you use the select CI or some other algorithms, they tend to very slowly converge. You need more configurations to get the same quality result. So there's something really interesting about LUCJ. And again, we sort of discussed this, right? If you have an ansatz that can actually pull out the most relevant configurations and ignoring the deadwood, then that could be a benefit of this. So what do results look like? This is a 27-qubit simulation. The figure here on the right is the layout on the IBM quantum hardware. Again, it's an Eagle device. This is a 27-qubit simulation, again, using OGCCPVQZ basis set. This is our active space, so it's 16 electrons, 12 orbitals. This is the water dimer. This represents the alpha electrons. This represents the beta electrons. The one thing that's really interesting to notice on this is this electron, there's 3 qubits between this one and this one. So these aren't particularly entangled. So we have these ancilla qubits here. So there's 3 points of strong entanglement, if you will. So there's a lot of interesting technical features here. Each quantum device, so IBM Cleveland has a little bit different error pattern than IBM Yonsei. So Yonsei is going to have its own kind of error patterns of its qubits. So each machine has its own personality, right? So again, these are all done in IBM Cleveland. So this is the layout here. Again, there's some interesting features that I don't won't really go into. Methane dimer, this is 36-qubit simulation. OGCCPV QZ base set again. It's a 16 electron, 16 orbital problem. And again, you have the alpha and beta electrons. In this case, I believe there's 1, 2, 3, 4 ancillobits that entangle the alpha and the beta spin. Oh, by the way, this paper just came out in arXiv maybe a week or two ago. So if you're interested, there's the arXiv. You can go ahead and download it. So what are the outcomes? So if you look at the potential curves on the top left, let's look at water dimer. SQD results and heat bath CI, one's in orange, one's in red. You can't tell them apart because the heat bath CI and SQD match perfectly. So basically the results we get from the classical hardware matches the quantum within 10 to the minus 4 kcal. The blue curve is CCSD full calculation, so not within an active space. And you can see that the overall our curve matches pretty well. There's about a half a kcal difference or so between the gold standard result using OGCCPV QZ base set and CCSD parentheses T calculations. But again, and as I'll show in the methane dimer, the issue here isn't the quantum device. The issue here is the choice of active space. In the case of the methane dimer, you can see the CCSD in blue, in orange CCSD, a little bit lower level theory. And then you can see SQD, heat bath CI, and CCSD parentheses T using the same active space, 16 electrons, 16 orbitals. And you can see they track each other perfectly. So the problem here isn't the choice, isn't the quantum device. The problem here is the active space that we've chosen. If we could choose the full active space, we would essentially get the same result as down here. By the way, in terms of quantum utility, these particular calculations on the quantum hardware take about 12 hours. Again, just rough numbers. Most of the expense is these multiple CI calculations, not the quantum hardware. If you do just the straight heat bath CI calculation, that takes about 8 hours. So we're not quantum utility on this, but we're really close. And again, the problem is our CI calculations. So to really dig into this a little bit more, we did some more calculations. So that, again, I reproduced the top left, the same figure, but we actually then did some larger calculations. These are all done classically in different orbitals. So instead of 16 electron, 16 orbitals, we did 16 electron, 24 orbitals using these different levels of theory, heat bath CI. This is with perturbation theory, CCSD. And you can see we start getting this really shallow minimum built. And again, just really shows that the problem here is active space choice. In this case, we did 2S, 2P active space. This included 3S and 3P active space. So overall, the results here are really promising. We could actually do the calculations. We understand how they behave very, very well. But again, it's a far cry from a protein, right? So ultimately, we want to do this kind of protein system. Let's see if I can pop the movie again. And so today, I'm just going to tell you about most recent results we've done on larger systems. We are currently working on peptides and some larger systems. But again, I'm going to focus more on smaller. So we decided just to go after cyclohexane. It's a molecule I really love. It's got a rich conformational space. And so we wanted to see how well we can handle something simple like cyclohexane, a small organic molecule. These are test calculations. I'm going to show you they're using the STO3G basis set. So we're not going to use the large basis set. And we're also going to use fragment-based methods. And we, at lunch, after lunch, we discussed fragment MO methods. You could use FMO. We're going to use something called density matrix, DMET, density matrix embedding theory. I think Garnet Chan developed this. So the idea here is we take a fragment CH2, so we have 1, 2, 3, 4, 5, 6 CH2s, and then we use DMET to define the orbitals. So DMET's an orbital base, and so in red, I'm sort of indicating the potential orbitals that you would include in your calculations. We then take the core, the CH2, plus the entangled, they call it entangled, unfortunately, entangled orbitals, or the orbitals that most strongly interact with this fragment. We then do the calculation on quantum hardware. So with this, we can go, we've already done some drug-like molecules, and we're currently working on much larger kinds of systems. So there's a number of fragmentation approaches. We talked about fragment MO just a little while ago. I'm a big fan of divide and conquer. Both of these are kind of atom-based approaches, and I'm sort of density matrix embedding theory is growing on me. This is a orbital based, so it's a little less arbitrary. You have sort of a way in which to identify the orbitals that most interact with your fragment. So I think there's some real advantages here. So today I'm going to tell you about preliminary work we've done on DMET, on cyclohexane, and some other model systems. In this paper, we're working on it right now with IBM. We should publish it hopefully in the next few weeks. So how does this work? Again, it's a quantum-centric supercomputing. We take our molecule, we choose our fragments. Initially, first thing we need to do is Hartree-Fock calculation, again, to get the orbitals for the whole system. We choose our fragment orbitals. We use the Schmidt decomposition as a single value decomposition strategy to obtain the fragment plus its entangled orbitals. And you can think of it this way. This picture is not formally correct, but the idea is that you'll have a subset of orbitals that you're then going to put into the IBM quantum device that may not be ordered directly like this, but for each CH2, you'll have a collection of the occupied orbitals and then some unoccupied orbitals that we're then going to do the CI calculations on. We generate the FCI dump just like before. We use the LUCJ onsat on the quantum processing unit for each fragment. And so in this case, there's 6 fragments. So basically, if we have 6 quantum computers, we can do 6 of these at once. If we have 6 classical hardware, we can do 6 of the classical post-processing. So this is, again, trivially parallelizable. We then post-process as before on the classical hardware. But there's one other feature as we do this iteration to get to do the error mitigation. We need to optimize the global chemical potential, which is essentially the number of electrons in the total system. So we need to make sure that if we add fragment 1, 2, 3, 4, 5, 6 together, that we have the correct number of electrons for the whole system. So that's an extra part in the iteration that we need to do. So we've implemented this at Cleveland. Yeah, I mean, it was actually, it was fairly easy to do because there's lots of good open source software. And again, I think open source software is amazing. It really enables, so we didn't have to write this from scratch. So we just use sort of available software tools. Again, this is down, first system I'll show is just H18. We did 3 subsystems of 6 electrons each. This is a layout on IBM Cleveland. It's a 27-qubit calculation. I think these figures, unfortunately, are rotated a little bit relative to the previous ones, so I apologize for that. So we have the Hartree-Fock calculation for this. We have DMET SQD with 5K samples. So again, of 10, instead of 10, we're doing 5K samples. We have DMET full CI, and we have DMET CCSD. And you can see these results like overlay. The error is extremely small for this particular calculation. By the way, I believe this is maybe the largest sort of ring that's been done, hydrogen atom ring using quantum hardware, but I may have that incorrect. We can also compare to the full calculation, so the 3 fragments of 6 hydrogens each using different methods, and we can compare to the full CCSD parentheses C calculation. And you can see in this case, as we stretch the distance, we get some errors at the little bit longer distance, but around the minimum, the agreement is quite remarkable using this procedure. And again, this is just looking at the full calculation. This is using larger sample sizes up to 10,000 for the SQD calculations and DMET SQD. And again, you can see in this particular case, they match quite well. So, and this is again, a 41-qubit test run. And again, this is using STO3G. So this is not using AUG CCPV QZ for these calculations. So let's go to comparing for the cyclohexane. This is 32-gigabit runs. And what we have is here we have a series of conformers of cyclohexane. So chair, it has a chair conformation. It looks like you're sitting in a chair. You have a half chair. It's like a love seat where your feet are up and your back is sort of leaning against it. Twist boat. So a boat is where you've got the molecule sort of sitting like this, and you can twist it a little bit. So you have a twist boat, and then you have a boat conformation. So this is DMET full CI versus DMET SQD using 10,000 samples, STO3G basis set. And again, the agreement between the two calculations is quite good. This is DMET SQD versus CCSD parentheses T at the same basis set. And again, the agreement is quite remarkable. Okay, so just kind of in summary, in this particular case, VQE is not up to the task for this particular problem. So VQE is not the way to go to do these kinds of chemistry problems. SQD or SQST is very a powerful approach. And I think one of the most important things is that I think the VQE is thinking like you're running classical hardware, whereas SQD is really thinking of your quantum device as a Rolodex or something that contains all this kind of information and you're just extracting it. So it's a very, very different, you would never do that in a classical hardware, but on quantum hardware, basically when you load this LUCJ ansatz, all possible slated determinants are there. It's just a matter of pulling them off, right, in the most effective way. So I think SQD is an extremely powerful approach. It required rethinking about how to do these problems. As we leave this NISQ era behind, what does the fault-tolerant future hold? I think with this DMET, we're going to be doing peptides and even small proteins in the next few months. So I think we're already doing big systems. But now if we can do big systems with ultra-high accuracy, with large basis sets, I think it gets pretty exciting. And in my opinion, quantum computing has untapped potential that could really, in terms of the slides I showed you of the different machines, this could be the next big step forward in terms of what we can do in computer hardware. I think just imagine, let's be really optimistic. Say quantum hardware could do these calculations 1,000 times faster. What would you do with 1,000 times more capability to do these kind of calculations? What kind of problems could you address? I mean, that's what you should be thinking about. Let's be pessimistic. It's only 10 times or 100 times. Still, what would you do with 100 times more performance? That means like the CI calculations I was talking about, which maybe take 12 hours, they would take a few minutes. What could you do, right? So synthetic data sets from machine learning AI, for example. There's lots and lots of things you could do with this. So I really think my gut tells me that just like a grad student that got on a Cray computer and it was 500 times faster, just as a full professor getting my code going on a GPU and it was hundreds times faster, I believe quantum computing is going to have that same impact down the line, in my opinion. Okay, I may be over optimistic, and it's sad to hear a company went out of business, but the beauty is I'm in an academic environment, and I can experiment, and I can try, and it's not my company that's on the line. So I think it's really exciting. This is a picture of Michele Parnell. Some of you may know he's right here, but Paolo Carloni is a dear friend of mine. When I was a 25-year-old, I spent a summer in Florence, and I taught Paolo how to do MD simulations. He's now a leading researcher in Germany at Jülich, and I understand he's moving to Pisa now. But he wanted to take us out to the countryside in Tuscany and show us where he grew up. So we were staying at a quaint farmhouse out in the countryside. And we got out of the car, and there was this rainbow. And so I was like, quick, everyone get together. Let me take a picture of you. But really, is quantum computing at the end of this rainbow? I don't know. In America, we say at the end of the rainbow is a pot of gold, but maybe we'll get a quantum hardware. So, yeah, that's right. It's a good eye. It's a double rainbow. You can't really make it, but it's a double rainbow. So and basically it's red, yellow, red, RGB, and then it's RGB in the inverse here. So it's red, green, blue, and then this would be red, green, blue. So it's a double rainbow. But it's a great picture, and I think a very optimistic one in terms of the future of quantum computing. So again, I mean, it's just been amazing to spend some time with everyone. And again, my deepest congratulations to having this machine installed here and taking a leading edge in the quantum computing world. I think it's a very important forward-thinking view of things, and I hope to see great things and maybe even collaborate with some folks here. So thank you for your attention.
Thank you for your great lecture, and maybe the quantum computing will be and at the end of the rainbow. Yeah, I think. Yeah. And actually, we collected some questions at the registration stage, but I think the floor question will first start it. Yeah, start. And if anyone have any questions, just raise your hand, and we'll bring the microphone.
I think this is amazing. I did not
Thank
know
you.
about this squeezed at all. So
Yeah,
this
it's
is very
really-
promising. And so one of my colleagues were working on the protein folding dynamics, and they have a competition, biennial competition, protein folding. So how many qubits would you need to compete in the CASP competition?
Yeah, you know, it's an interesting question. So Dan Blankenberg, like we had mentioned, you know, he had the unfortunate situation where he was trying to do like protein conformational search on quantum hardware when AlphaFold came out, right? But you know, to me, it's like, again, think about it. So basically, if you could encode with some ansatz the conformational space of a protein molecule, all possible conformers are in there, right? So then it really becomes, do you have a Hamiltonian that it can pull off? So the LUCJ seems to pull off important configurations.
Yeah.
So would there be a corresponding ansatz that would pull off important conformers of the protein molecule, relevant ones, or is there a way that you can pull off samples and do post-processing? So I don't know the answer. Like the way he was trying to do it, like lattice model, but I think, you know, there must be some way to have like a continuous function of torsion. So I think there's still some thought that needs to go into like how you can do conformational search. But in principle, if you could get all the material together, you should be able to extract conformations. And if you could come up with a good representation like LUCJ for that problem, you may pull off the very best conformers. So I think it's a really, really interesting thing to try. I don't have any answers. And I think squeeze is really an interesting way to go for this.
Thank you so much for letting us know this. Thank you.
Yeah, and I should be clear. I mean, squeeze was developed by Javier, Mario, and Antonio's team. And, you know, we were blessed to have an interaction with them. And so, you know, I feel very lucky to have been able to work with them. So it's a wonderful collaboration.
Actually, it's quite academic. So you have a hydrogen 18 cluster.
Okay.
So you try only a neutral.
Yeah, we didn't try
if
any
you put
charge.
one electron.
Yeah, yeah.
So I think, do you think are there any no problem for an ion?
Yeah, so the problem with DMET, and I think a lot of fragmentation methods, is like with DMET, you can use like 6UNG or CCPV-DZ seems to work okay. But as soon as you add diffuse functions, which are really important for anions, I think we would struggle. We have not done anions. Basically, we're just doing proof of concept right now. And then once we sort of work out all the bugs, get the paper published, we will go after, you know, other kinds of problems. But we may have to do anions. I don't think anions the problem so much. I think it's the diffuse functions, but we could certainly discuss
So some
that.
kind of a localization. Of
Yeah, I mean, so there could be different ways to go. You know, I don't And I think even with proteins, we're going to start getting into carboxylates. So would there be issues there, right? Using sort of representations that diffuse functions. So yeah, like localization or, I mean, to be determined, right? I mean, we're just, you know, like my group, we got this DMET working, we're just running on lots of different things, right? Because we have the hardware, you know, we have everything we need to do the calculations.
So another one is the quite practical. So actually, while we try, if you select the collaboration project subject, or in that case, I think this kind of quantum mechanical calculation will be for some period. It cannot be give us answer for the medical doctor's problem. So how about the machine learning? I think at this moment, machine learning will be a answer for that kind of collaboration.
Yeah, so so again, I think, you know, so I have a unique background, like from molecular simulation. And so we actually are using quantum hardware not in a drug discovery project yet, but we're using it to calculate the solvation free energy difference between two molecules using free energy methods. So there are tricky ways, it's called bookending. It's like a QMMM variant. So I think, you know, if things go well, I think we can integrate into drug discovery in the not too distant future within a QMMM structure. Now, whether that approach, you know, you take your drug molecule, you're going to do a free energy calculation, whether the quantum computing speed is sufficient, it may not be the case, right? But for like prototypes or just demonstrating future capabilities, I think we can already do it. So we literally are working on it. And we have several pharma companies that are very interested in collaborating with us for this kind of stuff as well. So I think it's not as far away as you might think. I think there's ways to do it. But it's using the quantum computer where it's good, and we're using force fields where they're good, right? That's the strategy.
I actually got one comment and one question. So
Sure.
the first comment is that you presented the performance of classical professors,
Right.
processors
Right.
per year. But one of the points is that the price actually per processor is getting lower, and the HPC center, the total flops of the HPC center actually still goes pretty the increasing exponentially. So it is not so easy for quantum computer to take away that kind of thing.
Yeah, you know, I think there's also, like, I'm a science guy.
Yeah. Sure.
I'm just trying to do cutting edge science, and in terms of the ROI, in terms of cost and power and cooling, you know, this is something I'm not worrying about, obviously. Sure. But it's in the end, it's going to be important. And I think there's, you know, again, for me, like, we have the pharma companies are interested. I mean, why on earth is a pharma? Because I think they're deathly afraid that this field will take off, and they're just holding the bag, right? Because I think a lot of them felt like they missed the AI machine learning completely, right? Even though there's sort of QSAR. So that's my sense when I talk to my colleagues, you know, in the pharma business, they're afraid to be left out, right? And it could be misguided, but by collaborating with us, it doesn't, if it fails, it fails, right? They didn't spend any of their money, you know, or hire people, right? So.
Yeah, so the one question is that,
But by the way, I mean, I think that's a great comment. I mean, it's something we should be thinking about. I'm not trying to downplay it.
Yeah.
Certainly the power considerations is
power
important.
So the other thing is that one question. So in your SQD simulation, the LUCJ, this ansatz is pretty important. But one thing I'm pretty nervous to ask is that whether such a circuit can be classically simulated. For example, like Professor Ganet Chan, their group developed lots of good classical algorithms for simulating quantum circuits.
Right.
Yeah. So if those type of circuits are also can be simulated using classically, then it'll be not really.
Yeah,
good
I mean, so
signal.
if say LUCJ has some magic associated with it, you can then simulate it, you know, using, say, a GPU, and you could get the same outcome. Like, you can get samples that are non-deadwood. So I don't have the answer for that. I mean, the person to talk to about that is Mario. Mario developed the LUCH Yonsei as I think a postdoc with Head Gordon. And so if you want to get into this kind of detail, I can connect you with Mario. You should talk to him. I think it would be a good conversation.
Yeah, thank you so much. Anyway, thank you for the great talk. Yeah, I'm pretty impressed.
Yeah. But again, I'm a scientist. I just want to see where I can go with quantum hardware, right? And I think all these, if you thought about like power considerations back when I was a grad student, you may have just quit, right? I mean, so, these things tend to have a way to take care of themselves, right? So, but excellent comments. And you can tell, it's probably your company gets those questions all the time, right?
So first of all, thanks for your fabulous lecture, and I really enjoy it, but I wish I can understand it fully because I'm undergrad, so.
Well, there's a famous quote, right? Yeah. The more you think you understand quantum mechanics, the least you understand of quantum mechanics. This is Richard Feynman, right?
Oh, yeah, sure.
So you're in good company.
Thank you. And my question is that why would you, if I understand it correctly, why would you implement the error mitigation in the post-processing stage instead of doing it during the execution?
Yeah, so there's different, like in the VQA world, there's different error mitigation strategies, and you can use those, and they do improve the outcome. But to me, I think the most amazing thing about this is you take the error mitigation off the quantum hardware and you replace it on the classical hardware, right? And it's also the nature of these Slater determinants. So to me, like one of the big innovations is this sort of error mitigation strategy, right? Off a quantum device. Because if you try to do it in quantum device, you probably would just keep getting more errors. By taking it off, you can sort of better control it.
Thank you.
Yep, great question. Thank you.
Thank you.
There is another online question. Yeah, it's by Park Yu-rang. How well did your interaction results predicted by quantum computing match the experiment data? And what additional validation method did you use to increase the reliability of your results?
Yes, that's a great question. So I should have brought this up. The water dimer experimentally is known to be about -5 kcals. CCSD parentheses T gets -5 kcals. So it matches, or 5.5. So basically the quantum calculations match experiment exactly, right? They're called chemically accurate calculations. For the methane dimer, it's like -0.5 kcals, and CCSD parentheses T matches experiment precisely. It's chemically accurate. So basically the quantum results in this methane dimer, water dimer, at the CCSD parentheses T match experiment completely. So they're entirely reliable. That was the first part. What was the second half of the question? Other error mitigation strategies?
How can you increase the reliability of your results?
So I think we touched a little bit on that. For the DMET, we can go to larger basis sets. For the hydrogen bond dimer and methane dimer, we can go to larger active spaces, are ways to increase the reliability. So I think on the dimer work, how to make it better is very clear. Bigger, the same basis set, but larger active spaces. In DMET, how do we improve it by maybe getting large, instead of SO3G, use larger basis sets, things like that. So again, how to do that is pretty clear. Now, whether it'll work, like in the case, you were talking about anions are more challenging. Maybe that would be difficult to correct. I don't know yet. We haven't done any work on that. But I think the ways to improve things are pretty clear, pretty straightforward, I think.
Thank you. Thank you for your thoughtful answers. And next, we have, it's running over late, but there was a prepared, that was a prepared question. If it's possible. Can
Yeah,
you
so
answer?
so insofar as quantum computing can improve, calculations in say computer-aided drug design, it doesn't matter whether it's a disease in South Korea or United States. It's going to make the ability to discover drugs better across the board, right? So again, if the quantum computing, say quantum machine learning or quantum chemistry, improves the ability to do drug discovery, then it's going to benefit everybody, whether you're from South Korea or Michigan, USA. So I think that's the answer for that. And the beauty of like Cleveland Clinic, we have some projects which basically we can work on and then we translate them immediately to the bench. This is true in the machine learning AI. We're working on one study on shock, and the idea is that we would then build a model for them and they would then test it in real settings. So they would have a patient come in, they would input information into the model, have them make a prediction. The model wouldn't determine the patient's therapy at that point. It would just be another bit of information that they could look at. Because the way they decide on how to treat trauma in a trauma setting is it's usually a team approach. Like multiple doctors talk about what they should do. So that's just one example of like how we're trying to translate what we're doing into hospitals. This is an interesting question, right? And we talked about this at lunch. So AI is an algorithm. Machine learning is an algorithm. Quantum chemistry is an algorithm. Free energy methods are an algorithm. So AI is an algorithm while quantum computing is an enabling technology. So quantum computing is like a GPU. GPUs had a big impact, right? So that's an enabling technology. It happens to benefit AI. But, you think about, I was part of the generation where Pong, was like this first video game where you would just bounce a white ball between paddles, right? And GPUs came along to have more interesting gaming environments, right? But at that time, nobody thought they'd be good for AI, right? It was good for, having more exciting games. And now, GPUs are absolutely essential to AI. So down the line, would quantum computing evolve in that direction? I mean, that's to be determined. But again, quantum computing is enabling technology, hardware, and quantum computing could be great for certain problems and useless in other cases. So it's going to be just like AI, like GPUs. GPUs are good for certain problems, not so good for other problems. I don't know, did anybody else want to add? I think we had a good discussion at lunch about quantum computing versus AI. So.
Next question is regarding Korean situation. So if any Korean professor can answer these questions, just be willing to participate this answering.
그래서 이 질문은 연재한테 하는 건 아닌 것 같고요. 그냥 시간이 많이 지나서 혹시 이거에 대해서 뭐 말씀해 주실 분 있으신가요? 아니면 사실 이 질문은 지금 과기부 홈페이지 가시면 올해 4월 말에 나온 이제 퀀텀 이니셔티브가 이제 자료가 잘 돼 있습니다. 그리고 최근에 나왔던 이제 양자 과학기술 고도화 방안에 대한 것도 언론 자료로 공개된 자료이기 때문에 좀 보시면 될 것 같고요. 결국 이제 두 번째 나온 것 같은 저런 얘기가 계속 나오고 있습니다. 과연 굉장히 이제 기술 집약적이고 또 어떤 이 이노베이션 그리고 또 협업이 필요한 이 양자 컴퓨터 분야에서 과연 이제 정부 주도로 하는 것이 경쟁력이 있을까? 또 정부 주도뿐만 아니라 정부에서 이제 예산을 가지고 각 대학 아카데미아에 줬을 때 그런 경쟁력입니다. 근데 여기서 이제 중요한 것은 우리가 이제 양자 컴퓨터를 물리적으로 개발한다라고 할 때는 실질적으로 조금 어려움이 있을 수 있지만 실질적으로 저희가 양자 컴퓨터를 활용해서 할 수 있는 것들은 좀 다른 측면에 있는 것 같고요. 그게 이제 4월에 발표된 양자 퀀텀 이니셔티브 안에 보면 제일 중요한 거는 사실 이제 인력 양성입니다. 이제 퓨처 탤런트를 우리가 어떻게 길러내서 우리나라에서도 양자 컴퓨터를 활용한 이 다양한 아까도 이제 모두에서 말씀드렸던 것처럼 지금까지 풀 수 없었던 난제들을 이제 풀어갈 수 있는가 하는 것들이 이제 가장 중요한 거고 또 국제적인 협력에 대한 내용도 들어가 있고요. 또 양자 번역, 중점 번역에 대한 것도 국가가 양성화를 하고 있고 또 하나 이제 중요한 영역이 뭐냐면 궁극적으로 이제 소위 말하는 이제 킬러 애플리케이션, 즉 양자 컴퓨팅을 활용해서 우리가 어떤 문제를 도메인의 문제를 풀려면 결국은 이제 소프트웨어 그리고 알고리즘이 있어야 되기 때문에 그런 양자 알고리즘 그러니까 사용할 수 있는 그런 양자 알고리즘을 개발하는데 이 국가에서도 어떤 전략적인 이 투자 방침을 가지고 있습니다. 그래서 자세한 내용들은 여러분들이 이제 거기 들어가시면 도큐멘트가 굉장히 잘 되어 있기 때문에 확인하시면 될 것 같고 그런 측면에서 우리 대학 연세대학교도 이곳 국제 캠퍼스에 들어오는 이 퀀텀 컴퓨터를 하나의 이제 허브화를 하고 다양한 우리 이제 뭐 최근에 이제 이학배 교수님하고 우리 김기현 박사님 등이 노력을 하셔가지고 양자 컴퓨팅 과제를 우리가 수주를 했는데요. 거기서도 얘기하는 게 결국은 뭐냐면 그 양자 컴퓨터의 어떤 산업적 활용을 통해서 이 사회적 가치를 창출하는 것입니다. 그러기 위해서 다양한 이제 커네스 교수님도 이제 멀스 교수님도 비슷한 얘기를 하셨는데 이제 HPC하고 퀀텀 멀티 이제 퀀텀 컴퓨팅 들어와 이제 활용함으로 해서 우리가 이제 문제를 푸는 그런 측면에서 우리가 지향하는 방향도 그런 쪽이라고 생각하시면 될 것 같습니다. 결국은 이제 다양한 이 퀀텀 컴퓨터 이제 플랫폼을 활용을 해서 우리가 문제를 풀 수 있는 이 다양한 이 알고리즘들을 개발하고 산업화를 조금 더 이제 산업 생산성을 고도화할 수 있는 쪽으로 이제 가려고 하고 있습니다. 답변이 이제 불충분할 수 있지만 좀 보시고요. 우리 그 김재원 원장님께서 이제 추가로 좀 코멘트를 해주시겠습니다.
예, 우선 정부에서는 그 7가지 전략을 세우고 있는데 첫 번째가 퀀텀 워크포스입니다. 거기에 해당하는 분들은 여기 계신 젊은 분들이고 또 사실은 우리나라에 이미 삼성전자라든가 현대전자라든가 LG라든가 여러 엔지니어들이 많이 있습니다. 이런 분들이 조금만 전환을 하면은 양자 기술적으로 넘어올 수 있다. 그게 가능합니다. 그 다음에 또 여기 연세대학교에 학부생들이 양자 정보 관련한 그 동아리를 만들었습니다. 퀀텀 인포메이션 연세 어카데미라고 QIYA라고 만들었는데 여기서 11월 1일부터 11월 15일까지 퀀텀 키스킷 폴 페스트를 합니다. 키스킷은 IBM 양자 컴퓨터를 쓰는 사용하는 소프트웨어고 그리고 그 이 학생들이 QIYA에서 그 IBM 양자 컴퓨터를 쓰는 들어가는데 필요한 그 뭐 아나콘다를 설치하고 그다음에 키스킷 설치하고 그다음에 비주얼 스튜디오 설치하고 이렇게 해서 어떻게 양자 컴퓨터에 접속하느냐 하는 데까지 매뉴얼을 만들어서 아마 학생 여러분들한테 제공할 것 같습니다. 그래서 11월 1일 날부터 시작하는 이 키스킷 폴 페스트에 많이 참여해 주시면 양자 컴퓨터 여기 계신 분들은 다 무료로 쓸 수 있으니까 많이 애용해 주시면 감사하겠습니다.
You know, if I could just pipe in, I think, you know, education, you hit all these, right? So you need to have the educated workforce. But there's two components, right? There's the hardware side, and Korea is famous for nanotechnology and all this, right? So you could get into the hardware game. But I think the other thing, too, is there's a dire need for software, right? And we were just discussing different things about software. So you could also work on the software and provide tools to the worldwide community, you know, allowing people to do this kind of work, right? So that's another aspect of it, right? It's a wide open field right now, so almost anything you can do, you're going to contribute, right? And I think Korea is particularly well placed in both hardware and software side. So just my opinion. So.
Thank you, Professor Morris. for your insightful response and for sharing your expertise with us today. Your lecture has provided us with a new perspective on the future of quantum computing in biohealth. I also want to extend my gratitude to all our attendees for your engagement and excellent questions. This concludes today's 9th Quantum Computing Biohealth Forum. We hope you found the session valuable and inspiring. Thank you for joining us today. And next, we are going to take a picture on the stage, yeah? And